Okay, so in this video we're going to do another measure theory related problem. And this is answering the question of if the measure of your space is equal to 1, what is the limit of the p-norm of a function as p goes to 0? And it ends up being this interesting expression here. And we want to show that this is true for any function that has a finite r norm for at least one r greater than 0. So this is not super easy to show, but we can get started. So the first thing that we can do is we can rearrange this expression a little bit. So if you take the log of both sides of this, so basically it would be enough to show that the log of this limit is equal to this integral log absolute f d mu. And by continuity of the logarithm, it would be enough to show that the limit as p goes to 0 of the log of the p-norm of f is equal to the integral of log absolute f d mu. So far we're just rearranging stuff, but this will be helpful later. And of course, what is the p-norm of f? The p-norm of f is, by definition, the integral of f to the p in absolute value raised to the 1 over p power. So all of this is inside of this log. And so that means that we can take this power out. So it's enough for us to show that the limit as p goes to 0 of 1 over p log integral absolute f to the p d mu is equal to integral log absolute f d mu. Okay, so this is kind of like our goal expression. So if we can show that this is true, then we're basically done. But what do we know? Well, basically we know that we know that integral log absolute f to the p d mu is less than or equal to log integral absolute f to the p d mu. And we know this by Jensen's inequality. So if you have a convex function, the reverse of this is true. The log of the integral is bounded by the integral of the log. So if it basically just if you have a convex function, the phi of the integral of a function is bounded above by the integral of phi of that function. So that's Jensen's inequality for a convex function. This is Jensen's inequality for a concave function instead, namely log of x. Okay. So this expression looks kind of like this one. In particular, if we bring this power down, so if we bring the p down and we rearrange a little bit, we see that this is the same as 0 is less than or equal to 1 over p log integral absolute f to the p d mu minus integral log absolute f d mu. So again, remember, we're trying to show that this limit up here is true. And we've just shown that this expression here is always non-negative, so it would be enough to show that this expression converges to 0. And because it's non-negative, we can do that using the squeeze theorem. So we want to bound this above by something. Okay, so now we want to think about some kind of clever inequality that we can use to get an upper bound on this. And one inequality that is useful in this case is this inequality, or equivalently log t is less than or equal to t minus 1. So this is true for like positive t or whatever. And we can apply that to this expression, right? So this is bounded above because here we have the log of an integral, so we can bound it above by that integral minus 1. So we have 1 over p integral absolute f to the p d mu, subtract 1 from that, minus this integral right here. Okay, so this is the expression that if we can show this goes to 0, then we are done, because it'll imply that this expression right here goes to 0. Okay, so everything we've done so far, we've basically just reduced the problem to showing that this expression right here converges to 0. And this is equivalent to the original thing that we were trying to show. Great. And here we want to use that the measure of the space is equal to 1, because 1 is equal to the integral over the whole space of 1 d mu, right? This is equal to 1. So another way to write this expression is 1 over p integral absolute f to the p minus 1, all of that d mu, minus integral log absolute f d mu. And then we can combine our integrals. This is the integral absolute x absolute f to the p minus 1 over p minus log absolute f d mu. Okay? So we basically want to show that as p goes to 0, this integral goes to 0. Okay, and we can do that using the dominated convergence theorem as follows. So we can first observe that if you take the function x to the p minus 1 over p minus log x, using L'Hopital's rule, it's pretty easy to see that as x goes to 0, or actually as p goes to 0, this goes to 0 for any non-negative x. And so clearly the thing inside of our integral is going to 0, okay, as p goes to 0. And so by the dominated convergence theorem, it's enough to show that the integrand here is bounded above by some integrable function. Because if you're taking an integral of a sequence of functions, that sequence is bounded above by something integrable, then you can interchange the integral and the limit. Okay, so that's what we want to do here. Okay, but now we can notice that if p is small enough, well, what can we really say about x to the p minus 1 over p? Well, if you think about it, this is just the integral of, so this would be the integral of y to the power of p minus 1 dy, integrated from 1 to x, right? And this is true whenever x is greater than or equal to 1. This expression certainly holds. And because y to the p minus 1 decreases as y increases, you can see that actually this is bounded above by x minus 1. Right, so this is bounded above by x minus 1 whenever x is greater than or equal to 1. Or, you know, you could, if you want, you could put absolute value bars there and it wouldn't really matter. So that's nice. And again, this is true as long as p is small enough, as long as p is less than 1. And so then the other case would be if x is less than 1, what can you say about the expression, this expression right here? Well, now this is the integral from x to 1 of the same thing. But now, again, if you just kind of think about this for a while, you can bound this above by integral from x to 1 of y to the negative 1, right? Because you're assuming that p is something non-negative. So you have y to the negative 1 dy. And what is this integral? Well, it's actually just negative ln x. So you get negative ln x here if x is less than 1. So those are kind of like your two cases. So what you can say about the function, so you have absolute f of x to the p minus 1 over p minus ln absolute f of x. And so this is really bounded above by one of two things depending on how large absolute f of x is. So if absolute f of x is at least 1, this is bounded above by absolute f of x minus 1. So there's kind of like two cases, right? So like if absolute f of x is greater than or equal to 1, and then otherwise this is bounded by negative ln absolute f of x if absolute f of x is less than 1. So another way to say this is that if you let E be the set of points for which absolute f of x is greater than or equal to 1, then you can say that this expression here is no larger than what? Well, it's no larger than absolute f of x minus 1 times the characteristic function of E, and then minus natural log absolute f of x times the characteristic function of E complement. And oops, I ran out of room. Okay, characteristic function of E complement. Great. So really the point here is that the function that we're integrating is dominated by something that is in fact an integrable function. And so that allows us to interchange the integral with the limit. And so it allows us to say that this integral log absolute f, that this goes to 0 as p goes to 0. And if we go back, basically all of this was equivalent, right? So just going all the way back to the beginning, all of this was equivalent to this identity here. This is what we were originally trying to show. So here I implicitly assumed that the integral of log absolute f, so I assumed that this was a finite value. So there's not like some large measure set where the absolute value of f is 0. In that case, you sort of have to apply a different argument, and I think I might leave that for another video because it's similarly very complicated. But yeah, so that completes the proof of this claim. So thank you for watching.